use it with. But if you are doing Newton's law of cooling before you know calculus, somebody else has done the calculus part for you and given you a longer, more complicated formula, and then you're using that. Obviously, we want to do this from the calculus perspective because that is the class that we're in and we have to do. So, Newton's law of cooling states that the rate of heat loss of a body is directly proportional. And a body here does not necessarily mean human body, but it can mean human body, and is one of the primary things that it is used for in like forensic stuff. So the rate of heat loss of a body is directly proportional to the difference in the temperatures between the body and its surroundings. Okay? So we need some different variables to use here. I would use, let's see, what do I usually use? Capital T. Let's let that be temperature of the body. Let's let T sub A be our ambient temperature. And K is going to be our constant of proportionality. K is just a constant number that we've got to find. So the rate, oh, and we need to let T, lowercase t, be time in this case. So the rate of heat loss of a body. So we're talking the rate of heat loss of the body. What is that going to be? It's the derivative of which variable? Capital T. So we're going to have, it's a little bit weird. Sometimes I don't use both variables like this. D capital T, which is temperature, over D lowercase t for time, is directly proportional to, if something is directly proportional to, that means there's a constant times whatever it is, right? So that's going to be K, that's our constant of proportionality, times the difference in the temperatures between the body and its surroundings. We're going to use the T of A, but it's the difference between the body temperature and the surrounding temperature. Difference tells us to do what? Subtract. So you're going to have capital T minus T sub A. Okay? This is your law for Newton's law of cooling. When Coach Wood gave you the equation, it looked a lot different because it had already been solved. Right? He didn't give you a differential equation for that because you weren't in calculus yet. So this is your differential equation for Newton's law of cooling. Any Newton's law of cooling problem, we can start from this. We're not going to have time in this unit because we're already testing while half of you are gone. Even though we might can do this while the half of you that are gone. Sorry guys that are going to be gone. Sometimes I do like a pizza roll lab, and we go microwave pizza rolls in the microwave in there. And pizza rolls are pretty much molten lava on the inside. Unless you don't microwave enough, then they're still frozen. Whenever they come out of the microwave, and you need to let them cool. And the package says let them cool. For like 2 minutes or something. But you can also use Newton's law of cooling to find when your pizza rolls are going to be at the perfect eating temperature. Or you can be like Daniel Bautista and be a man and eat them as soon as they come out of the oven and just go ahead and scald your mouth. Huh? Oh gosh, I've got it in the lab. I want to say like 140, 130
degrees Fahrenheit.
You want your food to, you don't want it 98 because then it's just like body temperature and it doesn't feel like it's warm. So, yeah. There could be some preference there. It's definitely not going to be. All right, we need to finish this problem. We might have enough time though while y'all are gone to eat some pizza rolls maybe. Y'all will be having fun without us, so we'll have fun without y'all just a little bit. All right, this is, your probably most interesting situation is to look at Newton's law of cooling from a forensics perspective, because if a dead body is found in a walk-in cooler in a restaurant at 6 a.m., when the first employee arrives, the cooler is kept at a constant 35 degrees Fahrenheit. When the body is found, it has a temperature of 72 degrees Fahrenheit. 20 minutes later, the temperature of the body is 65 degrees Fahrenheit. Estimate the time of death. Assume the person had a normal body temperature of 98.6 degrees Fahrenheit while alive. So what happens, though, is it's proportional to the difference. So whenever something is hotter, it's going to cool off faster. But as it cools, the difference between the temperature and the ambient temperature is smaller, right? So like if you take a Hot Pocket out of the microwave, it might be 180 degrees, right? And it is going to cool off pretty fast in those first couple minutes, but then that rate sort of slows over time. Because as it gets closer to the ambient temperature, it's going to not cool as quickly there. So it's not going to be as simple as like, oh, well, it dropped 7 degrees in 20 minutes, so we can just like go backwards. It's not going to be a linear relationship, so we can't just figure it out like that. So what we're going to have to do is we're going to have to start with our Newton's law of cooling. So we got d capital T over dt is going to equal K times T minus, there is one number that we can go ahead and plug into this. And that is our ambient temperature because it is a constant 35 degrees. If you are doing this, if you're doing these types of things, it is much more convenient for you if the person is found in a temperature-controlled environment. Because if they are outside on a hot day and are there till the cool night, your ambient temperature is also changing. So that is going to complicate things a little bit. But if they're in a walk-in freezer that is at a constant rate, then that is going to make your life a little bit easier as far as this goes. So you want to solve this for capital T. We want to solve this equation for capital T. So we're going to multiply by dt. Here, so we're going to get d capital T equals K T minus 35. We're not going to figure out. We're not going to solve the mystery today. We're going to run out of time. We're going to divide by T minus 35. Here. And so we will get, I'm going to write it this way, 1 over T minus 35 dt equals K dt. Okay, here. All right, now we need to integrate both sides. What type of integral are we going to have on that left-hand side? It's a u du. U is capital T minus 35. What's du? Just dt, right? So I've already got what I need here. This is just going to be the integral of 1 over u du, which means that when I integrate it, I'm just going to get natural log of the absolute value of u, which is T minus 35 there for that. What do I get when I integrate k dt? Close. Not kx, but very close. Kt, because t is our variable. So k lowercase t plus c. All right, is everybody with me here? All right, now, our lives will be easier if we solve this for t. So I'm going to do e to the power on both sides. That'll cancel over here. I'm going to get capital T minus 35. I'm dropping the absolute value bars because the C is going to take care of it here. Let's do a thinking bubble here so we don't have to do an extra line. This is e to the kt times e to the c, but what can we call e to the c? Just c, so we can write this as c e to the kt. So this is capital C e to the kt. And then we just add that 35. So t equals c e to the kt plus 35. And we're going to stop right here. We've got our differential equation solved, but obviously we haven't figured out the answer to the question yet, but we're out of time.